Intensive modern urbanization has stripped away almost all horizontal space. Cities prioritize raw square footage for human establishment, leaving zero ground for natural vegetation. Removing plant life creates an ecological dead zone. Without vegetation to absorb gases or provide shade, these concrete corridors trap heat, hold on to noise pollution, and aggressively degrade local air quality. To reclaim this lost capacity, architects and engineers are looking sideways. Vertical gardening expands the footprint of nature directly onto the sheer vertical planes of our buildings. The first blueprint to achieve this is the green facade. Here, the root systems stay firmly in the ground, or in large ground-level containers, while cascading plants are trained to climb specialized supporting structures that cover the wall. The second, more intensive architecture is the living wall. Instead of rooting in the ground, the entire system is built from pre-vegetated panels and planted blankets that snap directly into a structural steel frame fixed to the building. Living walls require a massive jump in mechanical maintenance, specifically for watering and fertilizing. By abandoning the ground, both frameworks allow vegetation to exist where horizontal space has been exhausted. The immediate enemy of any vertical structure is weight. Traditional soil is dense, holds heavy water loads, and exerts massive downward force, disqualifying it entirely for high-altitude planting. Engineering requirements for synthetic soil. The media must be nearly weightless, yet hold water and nutrients, requiring strict porosity and a neutral pH. The text below details the 3 distinct mechanical types of growth media used to meet those rules: loose, matte, and structural media. To manufacture these media types, builders blend highly specific, lightweight raw materials. The standard recipe combines cocoa peat, expanded perlite, sphagnum moss, vermiculite, and shredded bark. By stripping out the dirt and synthesizing a highly porous, nutrient-dense foundation, engineers successfully decouple the biological life cycle from the physical constraints of gravity. Because the plants have no access to ground aquifers, survival depends on an automated life support system. A drip tube network is woven directly into the multi-layered felt surface. An automation unit controls the exact cycles and injects nutrients directly into the flow. The system operates with extreme precision. While standard horizontal lawns waste massive amounts of water through evaporation and runoff, vertical systems consume between just 2 and 5 liters of water per square meter a day. A tall vertical surface rarely receives uniform sunlight. To prevent the shaded areas from drowning and the exposed areas from drying out, the irrigation grid is divided into independent segments, firing uniquely programmed cycles for each microclimate. Moving these walls inside introduces a severe energy deficit. Direct outdoor sunlight batters a wall with over 100,000 lux. Once you step into an average office building, that ambient light drops down to roughly 300 to 500 lux. Artificial lighting is mandatory, but it introduces steep physical decay. Light intensity drops with the square of the distance from its source. An indoor wall might hit 3,000 lux at the top near the fixtures, but fade to a weak 900 lux just a few feet lower.
Guaranteeing plant survival means meticulously mapping the shifting, invisible zones of moisture and artificial light before a single seed is planted. Botanical selection is dictated by exact spatial geometry. Operators require species that naturally grow incredibly dense and compact, hugging tightly to the framework. Placement is dictated by gravity. Because water travels downward through the structural media, the bottom of the unit holds significantly more moisture than the top, requiring distinct plant species depending on their vertical elevation. Shaded, low-light indoor environments require shade-loving herbaceous perennials like begonias and syngoniums. Operators fill the lower, damper tiers with ferns like Nephrolopus, while utilizing tough shrubs to fill out the drier sections. This table illustrates the hardier biological classes required for brutal exterior conditions. Outdoor facades rely on deeply resilient succulents like jade plant and sedums, alongside tough ground covers and grass-like foliage that can withstand high winds and direct heat. Building a vertical garden requires treating the plants themselves as hardware components, carefully inserting perfectly adapted organisms into their exact required slot within the machine.
When you scale out from the microscopic media and the drip lines, you see the completed architectural mechanism. A sheer drop of steel and glass is converted into a towering biological engine. The dense biological layer operates as physical armor. It absorbs ambient noise, provides thick thermal insulation against hot and cold air, and physically protects the exterior from extreme weather fluctuations, extending the structural life of the building. The local ecosystem sees immediate returns. The wall absorbs heated gases, filters out atmospheric pollutants, boosts oxygen production, and captures heavy rainwater to provide shelter for urban wildlife. This thermographic map highlights a critical citywide function. Standard exposed concrete traps radiation, generating extreme urban heat islands. The dark blue footprint of the living wall actively mitigates this, drastically lowering external temperatures block by block. These systems function as active protective infrastructure, shielding the urban grid from heat and sound while regenerating local air quality. Because they sit totally divorced from natural ground ecosystems, living walls demand strict human intervention to prevent the biology from collapsing. The mechanical structures must be constantly cleaned. Drainage disposal systems require daily oversight to prevent catastrophic water backups, and operators must rigorously prune the foliage and clear dried detritus to prevent rot.
High wind points along the facade require sanguine-specific triage, placing hardy succulents into the airstream to block damage. Nutrient tanks must be refilled and monitored perfectly to match the growth cycles. All of this requires highly skilled labor and expensive hardware. The initial construction and the relentless specialized maintenance mean vertical gardens carry a significantly higher price tag than standard horizontal landscaping. Cities that choose to pay the necessary premium buy immediate ecological capacity. By engineering glass and concrete to carry organic life, we maximize our vertical borders and transition dead urban airspace into a breathing ecosystem.